Math 1332, Chapter 3, Symbolic Logic, Section 2, Truth Tables, Video 1, Truth Table for Negation. All right, this is where we start building all the things that we need to determine the truth value of compound statements, not just simple compound statements, but larger compound statements that involve multiple logical connectives and possibly negations. And when we learn to determine the truth value of those statements, we'll be able to do things like analyze whether or not a conclusion drawn from a set of premises is a reasonable and logical conclusion. But we got a ways to go before we get there. All right, so let's start by asking the question, what is a truth table? Well, you might imagine that it looks like a table, and it does, but instead of describing what it looks like, let's describe its purpose. A truth table is a table that determines the truth value of a compound statement. That didn't take long to find a typo. All right, I think I fixed all of them, including the ones underneath the yellow boxes. But I digress. A truth table is a table that determines the truth value of a compound statement based on all possible combinations of truth values for the simple statements contained in the compound statement. It may sound like a lot of words, but it's actually a pretty simple concept once you see it in action. To kind of get an idea of what we're going for here, let's consider the following compound statement. If I win the lottery, then I will marry my fiance. Now, notice that this compound statement is a conditional. It has an if-then. Its antecedent, which we informally defined in a previous video, but we'll formally define later in this video series. But the antecedent, the simple statement following if, is I win the lottery. And the consequent, the statement following then, is I will marry my fiance. Now, those two individual statements have truth values. I win the lottery, that's either true or false. I marry my fiance, that's either true or false. And notice that I fiddled with the verb tense. Even though the simple statement is I will marry my fiance, we can also discuss it in the present tense. I marry my fiance, or even in the past tense, I married my fiance. So those two individual statements each have two truth values each. The first one is either true or false. The second one is either true or false. But that would give a possible 4 combinations of truth values for the pair. For example, suppose I win the lottery, making the first statement true, and I marry my fiance, making the second statement true. Is the compound statement true? In other words, is this entire statement true when both halves of it are true? But what if it's a different combination of truth values for the simple statements? For example, what about when I win the lottery, which means that the antecedent would be true, and I don't marry my fiance? I don't know why there's a stray A inside of that sentence. Let's make it disappear real quick. All right. So what about when I win the lottery and I don't marry my fiance? In other words, when the antecedent is true, but the consequent is false. And again, if you're a little bit lost on the use of the words antecedent and consequent, don't worry. We're going to define them formally later. Informally, antecedent is the first part of the if-then statement, and the consequent is the second part. Under that situation, is this whole compound statement true or false? 1 second, let's get rid of the T and F there. I was just going to undo it, but it would undo the typo that I corrected. There we go. All right, but that's an example of just to keep track of the truth value combinations we're looking at. In the first statement, was, in the first situation, the first simple statement was true and the second simple statement was true. In the second situation, the first simple statement was true and the second simple statement was false. So let's see what other combinations we can come up with. What about when I don't win the lottery and I marry my fiance? In other words, when the first statement is false and the second statement is true. Under those conditions, what can we determine about the truth value of the entire compound statement? And there's one combination of truth values that we're missing. Do you know what it is? What about when I don't win the lottery and I don't marry my fiance. In other words, the two halves of the conditional are false. This is false. I win the lottery, false. I will marry my fiance, false. Under that condition, or rather I should say those conditions, let's try this again. Will this conditional statement be true or false? And that's the objective of constructing a truth table, to be able to answer the question, when will a compound statement be true or false based on the truth values of the simple statements it's made of? Now, that's a lot to do, but we only need a few tools to pull this off. So what are those tools? Well, in order to be able to build truth tables for compound statements in general, we need some tools first. One that oh gosh, I really need to proofread these things better before I start the video. All right. As I was saying, we're going to need some tools to build these truth tables. One tool we need is the hierarchy of logical connectives. I think that's worth highlighting. Hierarchy of logical connectives. This will occur over and over and over as we build truth tables. This is similar to the order of operations for arithmetic, which some people know as PEMDAS, which is just a gimmick for the phrase, for the words parentheses, exponent, multiplication and division, addition and subtraction, the order in which you do arithmetic when you have more than one operation. Well, there's something similar for logical connectives called the hierarchy of logical connectives. And there are 5 things in that hierarchy. The first thing, which may not surprise you, are parentheses. Anytime you see parentheses, you're going to go inside them first. The second one is negation. The third one is actually a pair. It's conjunction and disjunction from left to right, although there will usually be parentheses to determine the order. The fourth one is conditional, and the last one is biconditional. So when we're constructing a truth table, the hierarchy of logical connectives will dictate the order in which to set it up. Once we get all the tools built, then I'll go over real detailed how to set up a truth table. Just a warning though, some textbooks and authors omit the first one parentheses under the assumption that it's obvious. I do not. In fact, if you look in the textbook that I'm currently teaching from, the author does not put parentheses first. I feel like it should go there, even though it's somewhat obvious. You want to, the best way to communicate math is to make it impossible to misunderstand. And by not putting parentheses first, you've opened the door for misunderstanding. All right, so this is one of the tools that we need, the hierarchy of logical connectives. And in case I didn't stress it enough, this is not going away. Learn it, learn it, learn it, learn it, learn it. Now, even if you write it down or refer to your notes, the less stuff you learn and memorize, the more time you have to spend every time you do a problem to look up something. If you know something is going to show up repeatedly, commit it to memory, and that will save you a lot of time when you do your homework in the future. It's not bad to look at it later or look at it again for reference, but you really need to memorize parentheses, negation, conjunction, disjunction, conditional, biconditional. I have told people in the past, I'm going to give you a test question. It's going to be, give me this list in this order. And you know how many people miss it? A bunch, even though I tell them this is a test question. So I'm not saying it's going to be a test question for your class, but don't be surprised if it was. All right, so what other tools do we need? The next tools we need are truth tables for negation and the logical connectives. Recall in the previous series of videos, we discussed conjunction, disjunction, conditional, biconditional, and negation. Technically, negation is not a connective because it does not connect to simple statements. It simply sits in front of one. But we will need a truth table for that, and we're going to start with negation's truth table. All right, now this truth table is empty, and this one is the smallest one you will ever see. It has 2 columns and, 2 columns and 3 rows. When you build a truth table, the last thing that you put in it, in the top row, is your final statement. The statement that you are trying to analyze the truth value of. And since we're discussing negation generically, we're going to say that our final statement is negation of P. Oh, by the way, I did go into a Facebook group and ask, why is P the most common letter to use for a generic statement in symbolic logic? There were a lot of speculative and goofy answers, but the most serious answer that I saw was logic at a higher level is actually called propositional logic, and statements are called propositions. So the conjecture is that P is short for proposition. That's the best answer that I had so far. I don't know if it's the correct answer, but it's the one I'm going to go with. Logic at a higher level being called propositional logic, statements being called propositions. Anyway, the last column in a truth table is always the symbolic representation of the compound statement that you're trying to find truth values for. Then you build up to it. You start with the simple statements that the compound statement is made of. Now, the only simple statement referred to in negation P is just P. So this will only have two columns. One for the simple statement that we're building on, and one for the I say compound statement, one for the final statement that we are ending with. No other truth tables will have only two columns. Now, as far as the rows, remember that the purpose of a truth table in this first paragraph here is to determine the truth value of a compound statement based on all possible combinations of truth values for the simple statements. So the only simple statement we have is P. And what are the possible truth values it can assume? Well, either a simple statement is true or it's false. This truth table only has two rows in addition to the top row. Most truth tables will have 4 or 8 rows. This is the only one that has 2. All right. Now that we have all the possible truth values of the simple statement listed, we need to ask ourselves, what's the truth value of the final statement, negation of P? Well, recall that the definition of a negation of a statement is a corresponding statement with the opposite truth value. So if a statement is true, its negation must have the opposite truth value, which is false. And if a statement is false, then its negation must have the opposite truth value, which is true. This is the truth table for negation. You can memorize it, but I would rather you understand it. Now, for every basic truth table that we're going to build, one for negation and one for each of the 4 connectives, each one is going to have a rule to follow, a verbal way of describing what happens in this truth table. So what is that rule for negation here? It's actually really simple. Negation changes the truth value of a statement. That is the rule for negation. That was supposed to be highlighted. Let's try it again. So you can memorize the table, and it's not that difficult. Right now, it may seem a little unfamiliar because it's our first truth table, but once we get through them, you'll look back on this one and go, that was easy. But I would also make sure you understand the rule. What negation does. Negation changes the truth value of a statement. In the next video, we're going to look at the truth table for conjunction. We'll build it, we'll come up with a rule for it, and consider it something that you need to memorize like this one here.